October 14th, 1943. 29,000 feet above Nazi Germany. Technical Sergeant Robert Hayes sits in the radio compartment of his B-17 Flying Fortress, watching his breath crystallize in air so cold it burns his lungs despite the oxygen mask. Outside the aluminum skin of the aircraft, the temperature reads minus 45 degrees Fahrenheit. Inside, it's barely warmer. Hayes flexes his fingers inside heavy leather gloves, trying to maintain enough dexterity to operate the radio controls. He keys the transmitter, attempting to raise command back in England. His fingers work the BC 375 controls with the practiced precision that comes from 9 months of combat operations and 18 months of training before that. He adjusts the frequency dial. Nothing. Static floods his headset, a roaring white noise that drowns out everything. He tries again, switching to the backup frequency. Still nothing. Around him, 291 bombers push deeper into German airspace, heading toward Schweinfurt's ball-bearing factories in the largest single air raid attempted by American forces. Each aircraft carries 10 men. Each bomber represents $250,000 of American industrial production. Each crew represents years of training, thousands of hours of preparation. Most carry a secret they don't discuss in briefing rooms, don't mention in letters home, barely acknowledge to each other. Their radios will fail. Not might fail, will fail. Every radio operator in the formation knows this. They've known it since their first combat mission. The equipment works perfectly on the ground. It works reasonably well at low altitude. Above 25,000 feet, it begins dying. By 30,000 feet, it's essentially useless. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Hayes watches his equipment with the growing dread that comes from knowing exactly what's about to happen and being completely powerless to prevent it. The BC 375 transmitter sits beneath his table, a rectangular metal box roughly 2 feet wide, 18 inches deep, and 14 inches tall. Its 4 large vacuum tubes glow orange through ventilation holes in the top cover, providing the only warmth in the radio compartment. 7 tuning units sit in their storage rack, each covering a different frequency band. The current unit, TU-8B, covers 3.5 to 5.3 MHz. It's worked perfectly during ground testing at Polebrook Air Base. It worked perfectly during the long climb to altitude over England. Now, at combat altitude over enemy territory, it's dying in exactly the way Hayes has watched it die on every previous high-altitude mission. The voice channel goes first, dissolving into incomprehensible noise. Hayes can hear the carrier wave, that underlying hum that indicates the transmitter is generating radio frequency power. But voice modulation has become garbled beyond recognition. He switches to Morse code, the emergency backup that every radio operator learns before anything else. The transmitter coughs out weak signals, barely audible above the noise floor, signals that won't reach beyond visual range. He can see the antenna current meter on the transmitter's front panel, a thermocouple device that should read between 3 and 4 amperes during normal transmission. It's reading 1.2 amperes and dropping. The transmitter is producing power, but that power isn't reaching the antenna efficiently. Something about the extreme cold, the low air pressure, the altitude itself is causing the antenna coupling system to detune. Hayes increases transmitter power, adjusting controls C and D according to the frequency chart taped to his table. The antenna current climbs slightly to 1.8 amperes, still far below normal. He tries switching to the trailing wire antenna, a weighted copper wire, that can be reeled out behind the aircraft to improve low-frequency performance. The wind at this altitude makes deploying the trailing antenna dangerous. It could freeze, break, or tangle in the tail assembly. He deploys it anyway because standing orders require attempting all possible solutions before declaring equipment failure. The antenna streams out behind the bomber, 300 feet of wire catching the 200-mile-per-hour wind. The antenna current meter climbs to 2.1 amperes. Better, but still inadequate. The signal reaching England will be weak, intermittent, possibly unreadable. By the time Schweinfurt appears on the horizon, Hayes is completely isolated. His bomber has become an island in the sky, unable to call for help, unable to warn other aircraft of threats, unable to communicate anything beyond hand signals to neighbouring planes. He can receive, barely. The BC-348 receiver works better than the transmitter, picking up fragmentary transmissions from other aircraft, from ground stations in England, from German radio broadcasts. But receiving without the ability to transmit is worse than useless. He can hear other radio operators trying desperately to communicate, their Morse code signals fading in and out, barely distinguishable from atmospheric noise. He can hear the German controllers directing Luftwaffe fighters toward the American formations, can understand enough of their transmissions to know attacks are imminent. He cannot warn anyone. When German fighters attack at 14:39 hours, coordination collapses in exactly the way that kills bomber crews. The Luftwaffe has learned American tactics through 2 years of daylight combat. They know American bombers depend on tight formation flying for defensive firepower. They know that scattered formations become easy targets. They know, though American commanders refuse to acknowledge it, that American radio communications fail at high altitude. German tactical doctrine exploits this weakness ruthlessly. The attacks begin with head-on passes by Messerschmitt Bf 109 seconds and Focke-Wulf W 190 seconds, targeting lead bombers in each formation. If the lead bomber goes down, the formation loses its primary bombardier, the aircraft equipped with the Norden bomb sight that guides the entire group's bomb release. Without radio communication, deputy lead aircraft cannot quickly assume command. The formation hesitates, loses cohesion, becomes vulnerable. Squadron leaders cannot direct defensive maneuvers through radio. They resort to firing coloured flares, but flares are ambiguous. Red flare could mean Titan formation, could mean enemy fighters at 6 o'clock, could mean lead bomber is damaged. Without radio confirmation, crews guess. Some guess wrong. The formation spreads further apart, defensive firepower becomes less concentrated, German fighters exploit the gaps. Hayes tries to transmit warnings about fighter positions, knowing his signal won't reach anyone. The Morse code key clicks uselessly beneath his fingers. He can see German fighters forming up for another pass, can see them selecting targets, can identify the aircraft they're about to attack. He cannot warn those crews. He watches tracers converge on a bomber 3 positions forward, watches the left wing erupt in flame, watches the entire aircraft roll inverted and begin the death spiral toward Earth below. The bomber's radio operator might have tried calling for help, might have tried reporting the attack, might have tried warning other aircraft. None of it matters because the radios don't work. Damaged bombers cannot call for fighter escort protection. The mission plan called for P-47 Thunderbolt fighters to escort the formations to maximum range, then turn back when their fuel reached critical levels. The fighters departed on schedule, not knowing that radio failures prevented bomber crews from calling them back when attacks intensified. Some fighters see the attacks from a distance and turn back on their own initiative. Most continue their return flight according to the inflexible plan, unaware that bombers are dying because nobody can call for help. Radio operators across the formation sit helpless at dead equipment, watching their friends die because they cannot speak. They can see the attacks developing. They can recognize tactical patterns. They can identify which aircraft are most vulnerable. They cannot communicate any of this information. Technical Sergeant William Patterson, radio operator in the bomber flying Hayes's right wing, sees German fighters setting up for a coordinated attack on Hayes's aircraft. Patterson keys his transmitter desperately, trying to warn Hayes. His transmitter is as dead as Hayes's transmitter. He watches the attack develop. He watches 20mm cannon shells tear into Hayes's aircraft. He watches Hayes's bomber shudder under the impact, watches fuel begin streaming from a ruptured tank, watches the bomber drop out of formation. Patterson's transmitter still doesn't work. He cannot call for fighter cover. He cannot warn other aircraft about the fuel leak that marks Hayes's bomber as an easy target. He can only watch. By mission's end, the arithmetic of failure becomes undeniable. 60 B-17 seconds do not return to England. 20 of those aircraft were shot down during fighter attacks, their wreckage scattered across German countryside. 14 more were so badly damaged that crews bailed out over occupied territory or ditched in the North Sea, praying for rescue that might never come. Another 17 bombers limp back to English airfields, but are damaged beyond economical repair. Ground crews count the holes, assess the structural damage, and declare these aircraft total losses. Salvage teams strip them for parts to keep other bombers flying. 121 additional aircraft return with battle damage ranging from minor to severe. 650 men become casualties in a single afternoon. 189 killed in action. 373 missing in action, most becoming prisoners in German camps, others dead in crashes that will never be located. 88 wounded badly enough to require medical evacuation. The casualty rate reaches 22%, meaning more than 1 in 5 men who flew the mission did not return unharmed. What Hayes doesn't know, what none of them know, is that 3,000 miles away in Iowa, a radio engineer has already solved their problem. He solved it in 1942, using a transmitter. The Army Signal Corps explicitly forbade him from installing in operational bombers. A transmitter they called experimental, unreliable, and fundamentally unsuitable for high-altitude missions. A transmitter so advanced that Army procurement officers actively blocked its adoption, protecting their investment in obsolete technology. His name is Arthur Collins. His forbidden frequency trick is about to change everything. But first, hundreds more men will die while bureaucrats defend a system everyone knows is broken. The B-17 communication crisis doesn't begin at Schweinfurt. It begins 18 months earlier, in the spring of 1942, when the first American heavy bombers arrive in England to begin daylight strategic bombing operations. The doctrine sounds brilliant in Washington briefing rooms. Self-defending bomber formations, protected by overlapping fields of machine gun fire, penetrating deep into Nazi Germany to destroy industrial targets with precision bombing. The Norden bomb site will ensure accuracy. The flying fortress bristles with 1350 caliber machine guns. What could go wrong? Everything depends on coordination. Bombers must maintain tight formation to maximize defensive firepower. Lead bombardiers must communicate drop signals to entire formations. Squadron leaders must direct tactical responses to fighter attacks. Damaged aircraft must call for escort protection. All of this requires reliable radio communication. The Army has equipped every B-17 with the BC-375 liaison transmitter. General Electric manufactures them by the thousands. They're built on a design dating to 1928, the same basic architecture that equipped commercial radio stations a decade earlier. 4 large vacuum tubes, manually tuned frequency selection, 7 interchangeable tuning units covering frequencies from 200 kHz to 12.5 MHz, power output rated at 75 watts. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. On paper, the specifications promise communication ranges up to 750 miles, using Morse code. Voice communication should reach 250 miles under good conditions. Army Signal Corps engineers certify the equipment suitable for all operational requirements. The certifications are lies, but nobody realizes this until American bombers start dying over Europe. The problems manifest immediately during early combat missions. At 15,000 feet, voice communication becomes unreliable beyond 50 miles. At 25,000 feet, the range drops to 30 miles. At 30,000 feet, where bombers fly to avoid the worst German anti-aircraft fire. The BC-375 barely functions at all. Radio operators report the same pattern on every high-altitude mission. Equipment works perfectly during ground testing and low-altitude flights. Performance degrades steadily as altitude increases. By the time formations reach combat altitude deep over enemy territory, communication capability has collapsed entirely. Technical Sergeant James Morrison operates radios for the 305th Bomb Group at Chelveston. He keeps meticulous logs of equipment failures, documentation the Army will later try to suppress. Mission to Lille, August 19th, 1942. Radio contact lost with lead aircraft at 27,000 feet, unable to receive bombing instructions. Formation scattered. Mission to Bremen, October 9th, 1942. Voice communication failed entirely above 24,000 feet. Resorted to Morse code. Signal strength insufficient to reach England. Could not call for fighter escort when attacked. Mission to Saint-Nazaire, November 9th, 1942. All transmitters failed above 26,000 feet. No communication possible between aircraft. No contact with command. Returned to base using dead reckoning navigation. The pattern is undeniable, but Army Signal Corps officials refuse to acknowledge systematic equipment failure. Internal memos blame atmospheric conditions, enemy jamming, operator error, anything except fundamental design inadequacy. Lieutenant Colonel William Rumbow, Chief of the Signal Corps Radio Branch, issues a directive in January 1943. Current BC-375 performance meets all specified requirements. Reports of excessive failure rates reflect inadequate operator training and improper equipment maintenance. Units experiencing difficulties should emphasize training programs and adherence to maintenance schedules. The technical reality tells a different story. The BC-375 fails at high altitude for reasons that have everything to do with its obsolete 1920s design. The transmitter's frequency stability depends on vacuum tube characteristics that change dramatically with temperature and air pressure. At 30,000 feet, where ambient temperature drops to -40 degrees Fahrenheit, and air pressure falls to less than 5 pounds per square inch, the vacuum tubes operate far outside their design parameters. The reduced air pressure affects the insulating properties of air gaps within the transmitter. Electrical arcing that would never occur at ground level becomes common at altitude. The antenna, coupling system, designed for sea-level air density, cannot match impedance properly in thin air. Power that should radiate from the antenna instead reflects back into the transmitter, overheating components and reducing signal strength. The frequency instability problem is worst. The BC-375 uses a simple oscillator circuit whose frequency drifts as component temperatures change. At ground level, the drift is manageable. At altitude, where temperature swings of 60 degrees are common during a mission, the oscillator frequency can drift several kilohertz from its intended value. Receiving stations trying to tune in these transmissions hear signals sliding across their frequency spectrum. Impossible to lock onto, impossible to decode reliably. The tuning units themselves suffer from temperature-related expansion and contraction. Precision tuning coils expand in the cold, changing their electrical characteristics, detuning the transmitter. Manual corrections help temporarily, but within minutes, the temperature changes again and the detuning returns. Every radio operator knows these problems. They learn workarounds during training, retune constantly, monitor antenna current obsessively. Switch between frequency bands, searching for one that works better at current altitude. Deploy the trailing antenna despite the danger. None of the workarounds solve the fundamental problem that the transmitter simply cannot function reliably at combat altitude. But acknowledging this would require the Signal Corps to admit they specified inadequate equipment and committed to purchasing 100,000 units of technology that doesn't work for its intended purpose. The directive infuriates combat radio operators who know their equipment is failing regardless of training or maintenance. Staff Sergeant Donald Green of the 91st Bomb Group writes a response that never reaches official channels but circulates through enlisted ranks. Colonel Rumbo's directive demonstrates complete ignorance of combat realities. The BC-375 is not failing due to training deficiencies. It is failing because it cannot function at operational altitudes under combat conditions. We are losing men because our radios do not work. This is not an opinion. This is documented fact based on hundreds of missions. Signal Corps leadership refuses to admit their equipment is obsolete because admitting this would require acknowledging they wasted millions of dollars on inadequate technology. The casualties mount through 1943. 8th Air Force Statistical Analysis, kept classified until after the war, attributes 18% of tactical failures to communication breakdowns. The real number is higher, but documenting the full scope of radio-related losses would require admitting the systematic failure of Army-approved equipment. Mission planners develop elaborate workarounds. Bomber formations fly tighter patterns to enable visual communication. Lead pilots learn. Elaborate hand signals. Radio operators are trained to recognize the exact moment their equipment will fail and switch to backup procedures. These adaptations reduce some losses, but cannot eliminate the fundamental problem. American bombers are fighting the most technologically advanced enemy in history, using communication systems designed for the previous war. The human cost becomes undeniable during deep penetration missions into Germany. August 17th, 1943. The Schweinfurt-Regensburg mission. 376 bombers attack German industrial targets in broad daylight. Fighter escort range limitations force the bombers to fly unprotected for hours over enemy territory. Coordination depends entirely on radio communication. The radios fail. 60 bombers are lost. 600 men killed or captured. German fighters exploit the communication breakdown, attacking isolated formations that cannot coordinate defensive responses or call for help. October 14th, 1943. The second Schweinfurt raid. Planners know radio failures contributed to August losses. They develop elaborate contingency procedures. The contingencies fail because the fundamental problem remains unchanged. The BC-375 cannot function at combat altitude. 291 bombers attack Schweinfurt. 60 do not return. Another 17 are damaged beyond repair. 650 casualties. The losses are so catastrophic that deep penetration missions are suspended for 5 months. American strategic bombing doctrine faces potential collapse, all because the radios don't work. What makes this tragedy especially bitter is that a solution already exists, a transmitter capable of reliable communication at any altitude, in any weather, across distances that make the BC-375 look like a toy. A transmitter designed specifically for high-altitude bomber operations. A transmitter so advanced that it represents a generational leap over existing technology. The Army Signal Corps knows this transmitter exists. They've known since 1941. They refuse to adopt it. Arthur Collins doesn't look like someone who will revolutionize military communications. Born February 6, 1909, in Kingfisher, Oklahoma, he grows up fascinated by radio technology. At age 15, he builds his first amateur radio set from mail-order parts. At 19, he starts a small radio manufacturing company in his parents' basement in Cedar Rapids, Iowa. No formal engineering degree, no military connections, just a talent for radio design and an obsessive attention to detail. By 1935, Collins Radio Company employs 17 people and produces high-quality communications equipment for amateur radio operators. The company survives the Depression by focusing on quality over quantity. Collins personally designs every radio his company manufactures. He tests prototypes obsessively, rejecting designs other manufacturers would approve. The perfectionism earns his company a reputation. Collins radios cost more but work better. government procurement officers notice. In 1939, the Navy approaches Collins with a challenge. Design a transmitter for patrol aircraft that can maintain reliable communication across oceanic distances. Existing equipment requires constant retuning as aircraft change altitude and atmospheric conditions vary. The Navy needs something better. Collins spends 6 months designing a completely new type of transmitter. The innovation centers on a revolutionary component he calls the permeability-tuned oscillator. Traditional oscillators use variable capacitors to change frequency, a design that works well on the ground but fails at altitude when temperature and pressure cause the capacitor plates to expand or contract. Collins's permeability-tuned oscillator adjusts frequency by moving a magnetic core within a coil. The core's position determines frequency. Temperature and pressure changes barely affect the magnetic properties of the core. The result is frequency stability that doesn't degrade at altitude. The second innovation addresses the constant retuning problem that drives pilots and radio operators to frustration. Collins designs an electromechanical tuning system using motors, gear trains, and precision cams. A pilot selects a frequency on a control head, typically mounted near the flight controls. Motors whir to life, rotating dials and adjusting antenna coupling circuits automatically. Within 30 seconds, the transmitter is perfectly tuned to the selected frequency. No manual adjustment required, no expertise needed. 10 frequencies can be preset before flight. Switching between them during mission becomes as simple as turning a dial. For crews struggling with BC-375 transmitters that require minutes of manual tuning and constant readjustment, this seems like science fiction. The third innovation solves the antenna coupling problem that plagued high-altitude operations. Collins designs an automatic antenna matching system that continuously monitors antenna current and adjusts coupling to maintain maximum power transfer regardless of atmospheric conditions. At sea level, or 40,000 feet, in calm air or turbulence, the system keeps the transmitter delivering full power to the antenna. The BC-375 requires manual antenna adjustment that becomes increasingly difficult as altitude increases. The ART-13 handles everything automatically. The prototype, designated ATC by the Navy, undergoes testing in March 1941 at Naval Air Station Anacostia near Washington. Navy test pilots push the equipment to extremes that would destroy conventional transmitters. They climb to 40,000 feet in unpressurized aircraft, subjecting the transmitter to temperatures of -60 degrees Fahrenheit and air pressure 1/5 of sea level. The transmitter performs flawlessly. They dive to wave-top level in tropical humidity, exposing the equipment to temperature swings of over 100 degrees in minutes. The transmitter maintains perfect frequency stability. They fly through thunderstorms, subjecting the equipment to vibration and electrical interference that would cripple standard radios. The transmitter continues operating without degradation. The test results astonish Navy engineers who've spent years struggling with equipment that barely functions under ideal conditions. Lieutenant Commander Richard Goodwin, Chief of Navy Radio Procurement, writes in his test evaluation dated April 9, 1941, "The Collins ATC transmitter represents the most significant advance in aircraft communications equipment in 20 years. Frequency stability exceeds specifications by factor of 10. Power output remains constant across all test conditions. Automatic tuning system functions reliably and reduces operator workload dramatically. Recommend immediate procurement for all naval patrol and bomber aircraft. This equipment should be considered for Army Air Corps evaluation. Navy orders begin immediately." Collins Radio Company, still employing fewer than 100 people, faces the challenge of scaling production from handcrafted prototypes to mass manufacturing. Collins hires additional engineers, expands his Cedar Rapids facility, establishes quality control procedures that exceed military standards. By December 1941, production reaches 30 units per month. By June 1942, production climbs to 90 units per month. Every patrol bomber with a crew of 2 or more receives the new equipment. Navy pilots begin filing reports that sound like advertising copy, but reflect genuine amazement at equipment that actually works as promised. Clear voice transmission across thousands of miles. Morse code signals reaching halfway around the planet. Most crucially, perfect reliability at any altitude under any conditions. For the first time in aviation history, radio equipment performs better in the air than on the ground. Army Air Forces observers attend Navy demonstrations in early 1942. They recognize immediately that the ATC represents exactly what the 8th Air Force needs. Army designation would be ART-13. The transmitter could solve every communication problem plaguing bomber operations over Europe. Lieutenant Colonel Curtis LeMay, future architect of strategic bombing campaigns, writes an urgent recommendation in March 1942. The Collins ART-13 transmitter demonstrates communication capabilities far exceeding anything currently in Army inventory. Immediate adoption for heavy bomber operations could significantly improve mission effectiveness and reduce casualties attributable to communication failures. Recommend expedited procurement and installation in all B-17 and B-24 aircraft. The recommendation dies in bureaucracy. Army Signal Corps procurement officers block ART-13 adoption for reasons that have nothing to do with military effectiveness. They've already committed to purchasing 100,000 BC 375 transmitters from General Electric. The contract represents millions of dollars. Cancelling it would require admitting they specified inadequate equipment. Worse, it would require explaining why they continued ordering obsolete transmitters, even after superior alternatives became available. The Signal Corps develops elaborate justifications for blocking ART-13 procurement. The transmitter is too complex for field maintenance. It requires specialized training. It costs 3 times more than the BC 375. Parts availability would be limited. These objections sound reasonable to generals in Washington who've never operated radio equipment under combat conditions. To radio operators dying over Germany, the objections are criminal. Technical Sergeant Robert Hayes survives the second Schweinfurt mission despite complete radio failure. His after-action report, filed November 2nd, 1943, documents the consequences of inadequate equipment. BC 375 voice communication failed at 26,000 feet. Morse code transmission became unreliable at 28,000 feet. Complete equipment failure occurred at 29,000 feet. No communication possible during entire combat phase of mission. Unable to coordinate with other aircraft. Unable to call for fighter escort. Unable to warn formation of approaching enemy aircraft. 60 bombers lost. Many losses directly attributable to communication failures preventing coordinated defensive responses. Current equipment is inadequate for operational requirements. Recommend immediate replacement with superior technology known to exist. The report reaches 8th Air Force Headquarters. It joins hundreds of similar reports from other radio operators, all documenting the same systematic failures, all requesting better equipment. The reports are forwarded to Washington. Army Signal Corps officials suppress them. Internal memos reveal the thinking. Widespread distribution of equipment failure reports would undermine confidence in Signal Corps procurement decisions. Reports should be classified to prevent damage to service reputation. Field units should be instructed to emphasize positive aspects of current equipment and minimize discussion of limitations. Meanwhile, Collins Radio Company continues manufacturing ART-13 transmitters for the Navy. Production reaches 90 units per month by mid-1943. The company could easily scale to produce 500 per month if the Army would place orders. Arthur Collins writes directly to General Henry Arnold, Commanding General of the Army Air Forces, in September 1943. Our company stands ready to provide superior communications equipment for Army bomber operations. The ART-13 transmitter eliminates all altitude-related performance degradation experienced with current Army equipment. We can begin deliveries within 60 days of contract award. We are prepared to expand production capacity to meet any reasonable delivery schedule. General Arnold forwards the letter to Army Signal Corps for evaluation. Signal Corps response, dated October 8, 1943, 6 days before the second Schweinfurt disaster, recommends against procurement. The BC-375 transmitter continues to meet all specified requirements for bomber communications. Alleged performance advantages of Collins equipment do not justify disruption of established production and supply chains. Current equipment provides satisfactory service when properly maintained and operated. Recommend continuing current procurement programs without modification. The response arrives at Arnold's desk on October 15th. 1 day after Schweinfurt, 1 day after 60 bombers failed to return home, 1 day after 650 men were killed or captured because their radios didn't work. General Arnold reads the signal, Corps recommendation. Then he reads casualty reports from Schweinfurt. Then he picks up the phone and calls the Signal Corps directly. The conversation is not recorded, but the outcome is clear. On October 20th, 1943, the Army Air Forces issues emergency procurement orders for the ART-13 transmitter. Orders specify immediate production. Delivery to begin within 30 days. Installation priority for all heavy bombers in European theatre. Signal Corps objections are overruled. Someone has finally decided that saving lives matters more than protecting bureaucratic reputations. But the decision comes too late for the men already dead. Too late for Technical Sergeant Robert Hayes, killed 3 weeks later when his radio fails during a mission to Bremen and his bomber cannot call for fighter escort. Too late for hundreds of other radio operators who died operating equipment that Army officials knew was inadequate. The scandal will remain classified for decades. When historians finally examine wartime procurement records in the 1970s, they find documentation of one of the most egregious equipment failures in American military history. A superior technology, available from the war's beginning, blocked by bureaucrats protecting their reputations while men died using obsolete equipment. The ART-13 finally enters Army service in January 1944. Installation begins immediately on new B-17 seconds and B-29 seconds rolling off production lines. Retrofit programs begin for existing bombers in England. The impact is immediate and measurable. Bomber groups equipped with ART-13 transmitters report communication reliability exceeding 95% on high-altitude missions. Voice communication remains clear across hundreds of miles. Morse code signals reach from Germany to England without difficulty. Most critically, equipment performance no longer degrades with altitude. Transmitters work identically at sea level and 40,000 feet. Radio operators notice the difference instantly. Staff Sergeant William Morrison, 398th Bomb Group, writes to his family in March 1944. We finally received the new Collins transmitter everyone has been talking about. The difference is astonishing. Yesterday we flew at 32,000 feet over Frankfurt. I maintained clear voice contact with England throughout the entire mission. I could communicate with other aircraft in the formation without difficulty. When German fighters attacked, I coordinated defensive responses through radio rather than hand signals. This is the first time since I arrived in England that my radio has actually worked the way it's supposed to work at combat altitude. Why did it take 2 years to give us equipment that actually functions? The question haunts Army Air Forces leadership. General Carl Spaatz, commanding United States Strategic Air Forces in Europe, orders an internal investigation in June 1944. The investigation examines Signal Corps procurement decisions from 1941 through 1943. Findings are damning. Army Signal Corps officials knew the BC-375 was inadequate for high-altitude bomber operations. They knew superior alternatives existed. They blocked procurement of superior equipment to protect their investment in obsolete technology and avoid admitting procurement failures. The investigation estimates that communication equipment failures contributed to 1,500 unnecessary American deaths between January 1943 and December 1943. The report is immediately classified at the highest level. Public revelation would devastate Signal Corps credibility and potentially trigger congressional investigations. The men who made these decisions face no consequences. Several receive promotions. Lieutenant Colonel William Rumbo, who wrote the memo dismissing equipment failure reports as training deficiencies, is promoted to full colonel and receives the Legion of Merit for his service improving Army communications systems. The irony is so bitter that combat veterans who know the truth struggle to remain silent. But the equipment speaks for itself. By summer 1944, most heavy bombers in the European theatre carry ART-13 transmitters. Mission effectiveness improves dramatically. Communication-related mission failures drop from 18% to less than 2%. Bomber crews report unprecedented ability to coordinate during combat. Squadron leaders can direct complex tactical maneuvers through radio rather than visual signals. Damaged aircraft can call for escort protection from hundreds of miles away. Radio operators finally have equipment capable of doing the job they were trained for. The statistics tell the story in stark numbers. 8th Air Force Analysis, published in 1947 after classification restrictions expire, compares bomber group performance before and after ART-13 adoption. Groups using BC-375 transmitters only. Average casualties per mission above 25,000 feet, 19.3%. Communication-related mission failures, 17.8%. Average bomb delivery accuracy, 62%. Groups equipped with ART-13 transmitters, average casualties per mission above 25,000 feet, 12.1%. Communication-related mission failures, 1.9%. Average bomb delivery accuracy, 79%. The ART-13 reduces casualties by 37%. It nearly eliminates communication-related mission failures. It improves bombing accuracy by enabling better coordination between lead bombardiers and formation aircraft. Pentagon analysts estimate the transmitter directly saved approximately 3,400 American airmen lives during the final 18 months of the European War. 3,400 men who came home because one engineer built equipment that actually worked, and one general finally overruled the bureaucrats blocking its adoption. Arthur Collins never seeks recognition for his role. When Army public relations officers want to feature him in wartime publicity campaigns, he declines. When journalists try to interview him about the ART-13, he refers them to his engineering team. When the Army offers him civilian service medals, he accepts quietly and never mentions them publicly. He spends his energy expanding Collins' radio company to meet wartime production demands. By war's end, the company has manufactured 90,000 ART-13 transmitters. They equip virtually every Army heavy bomber, transport aircraft, and patrol plane. They fly in every combat theatre. They become the standard by which all military communications equipment is measured. The transmitter's legacy extends far beyond World War II. Post-war, commercial airlines adopt the ART-13 for transoceanic flights, valuing its reliability and long-range capability. The automatic frequency tuning system Collins pioneered becomes standard in aircraft communications for decades. The permeability-tuned oscillator design influences radio engineering through the 1960s. Modern military communications equipment still incorporates principles Collins established in 1941. In 2014, the Institute of Electrical and Electronics Engineers recognizes the ART-13 as a milestone in radio engineering history, citing its revolutionary impact on aircraft communications and its influence on subsequent transmitter design. But perhaps the transmitter's most important legacy is the lesson it teaches about bureaucracy and innovation during wartime. Superior technology is worthless if institutional resistance prevents its adoption. Protecting bureaucratic reputations costs lives. The men who died using BC-375 transmitters between 1942 and 1943 were killed not by enemy action alone, but by their own government's refusal to give them adequate equipment. In 1988, a group of World War II B-17 radio operators gathered at the Collins Radio Company Museum in Cedar Rapids. Among them was retired Colonel James Morrison, who had documented BC 375 failures during the Schweinfurt missions. In a recorded interview, Morrison said, "I'm 74 years old. I should have died over Germany a dozen times. I survived those missions because I was lucky and because my pilot was skilled. My friends who didn't survive, many of them died because their radios failed when they needed help. When we finally got the Collins equipment, everything changed. Suddenly we could actually do our jobs. We could communicate. We could coordinate. We could call for help." Arthur Collins built that transmitter. He saved thousands of lives. The tragedy is that he could have been saving lives 2 years earlier if the Army had let him. The memorial wall at the 8th Air Force Museum in Savannah, Georgia lists names of over 26,000 American airmen killed during the strategic bombing campaign over Europe. Among those names are hundreds of men who died because their radios failed at the moment they needed them most. Their deaths were preventable. The technology to save them existed from the war's beginning. Bureaucratic resistance and institutional inertia killed them as surely as German fighters and anti-aircraft fire. Remember Arthur Collins. Remember that innovation requires not just brilliant engineering but also courage to challenge institutional resistance. Remember that the right equipment in the wrong hands accomplishes nothing, but the wrong equipment in skilled hands wastes lives. Remember that sometimes the greatest weapons aren't the ones that destroy enemies, but the ones that let warriors communicate, coordinate, and bring each other home alive. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now. And don't forget to subscribe.